Page 304, number 48. Ooh, we have a trig function. So, we're going to find the indefinite integral of x times the sine of x squared dx. Now, one of the ways we can use substitution on a problem with trig functions in your integrand is that the theta part of the trig expression can be the u. So, for instance, we can let u equal x squared. And if u does equal x squared, let's compute du. Well, what's the derivative of x squared? So if u equals x squared, then du equals 2x dx. And I think, no, we don't either, do we? So, I think we're done. We can do the substitution, but we're not quite there. All right, that I'm going to change to the sine of u, correct? Then I need to replace the x dx, and I almost have it. So what do I need to do to it? Divide by 2, multiply both sides by 1/2, either way. Because we have to replace x dx. So look what we can do now. We can rewrite the integral. We've got the integral. The sine of x squared. Since u equals x squared, that's now the sine of u. So I've taken care of that. But I can't write x dx down there with it because then I'd have u's and x's and dx's and everything's all confused. You know, no good. I've got to replace x dx so that I only have u's and du's in my problem. So that's the reason we solved. Well, we didn't. Well, we solved for x dx, didn't we? We wanted to replace x dx, so we solved for x dx. So x dx can be replaced by 1/2. I'm going to end up setting a constant out in front, du. So I've replaced x dx with 1/2 du. Now my problem looks like this. And as long as I can find the antiderivative of the sine of u du, I made a good choice. Well, can I find the antiderivative of the sine of u du? What is it? Negative cosine u plus c. So we have the 1/2 out in front still. Then the integral of sine u du is negative 1/2, or is negative cosine of u plus c. And like we talked about one day last week, I don't have to distribute the 1/2 times the c, although technically that's exactly what I would do, is that would be bracketed, that would be bracketed. But c is a constant that we don't know anyway, so if it bothers you, think of it as being c1 on this line, and then once we distribute the 1/2, it'll be c. Okay? So, there is something I need to change, though. What do I need to change? I want the negative in front of the 1/2. What else do I want to change? U needs to be rewritten as x squared. Are we happy with that? Yeah, I'm thrilled. Questions? All right, number 49. This time we have the integral of the sine of 2x cosine of 2x dx. So, let's pretend for a moment that the way we worked the last problem is the way we always work a problem that involves trig, in that we let the theta portion equal u. Do not write this down. If that were the case, then we would let u equal 2x, and then we'd say, well then du equals 2 dx. Okay, we don't have a 2, So we'd say 1/2 du equals dx, and we might be feeling pretty good about things. Then when we make the substitution, that'd be the integral. The sine of 2x would now be the sine of u. The cosine of 2x would now be the cosine of u. Dx would be 1/2 du. And then we'd say something like, hey, as long as I can find the antiderivative of the sine of u, cosine of u, du, I made a good choice. You compute it. Du is the derivative of that. Okay? So, can we find the antiderivative of the sine of u, cosine of u, du? No, we cannot. So, even though it worked out into a nice, neat little substitution, it led us to an integrand that we don't know how to integrate. So we better try something else. Well, on our guidelines, sometimes we let u equal a quantity with an exponent on it. I don't see an exponent, but I'm going to let u equal a quantity. I'm going to let u equal the sine of 2x. Which seems sort of strange at first, maybe. But then the question was just asked, how do we get du? We compute it. So du is the derivative of the sine of 2x with a dx thrown in at the end. Well, what is the derivative of the sine of 2x? Cosine of 2x times the derivative of 2x. It's the chain rule. It's the chain rule for differentiation. The derivative of the sine of u is cosine of u times the derivative of u. So the derivative of the sine of 2x is cosine of 2x times the derivative of 2x. Bizarrely enough, that's really good news, isn't it? Because look what's happening. Let's think ahead a little bit. That's going to be u, and then look, all of that's going to be knocked out with the du, isn't it? So it's really working out just perfectly. The only trouble is, got a little extra 2 there, so what do? We divide both sides by 2, and so that means that 1/2 du equals the cosine of 2x dx. And I think we're in really good shape now. Let's see if we are. Okay? So when I rewrite this integral, I'm going to have the integral. And then the sine of 2x, well, that's u. And then the cosine of 2x dx, well, the cosine of 2x dx is 1/2 du. So if I put the 1/2 in front, du, can I integrate that? Can I find the antiderivative of u du? It's u. I replaced the sine of 2x equals u, so when I wrote down, instead of writing down the sine of 2x, when I rewrote this, I wrote u. All right, so we can do this. So our new integral is 1/2 times the integral of u du. Keep the 1/2 in front. What's the integral of u du? 1/2 u squared plus c. You add 1 to the exponent. That's how you get the u squared. And then you divide your coefficient by the new exponent. Now, dividing the coefficient of 1/2 by 2 is a little cumbersome unless you do it in your head. So, instead of dividing by 2, I'm multiplying by the reciprocal. I'm multiplying by 1/2. And don't forget, plus c. So far, so good? Well, 1/2 times 1/2 is 1/4. And then instead of u in my answer, I want the sine of 2x to be u. So the sine of 2x, quantity squared, plus c. And the only thing, I have one small problem with this. That's not really the notation we use to square the sine of 2x, is it? 1/4 times sine squared of 2x plus c. All right? Number 64. This time, they have to give us a hint and tell us to use the method shown in example 5. Well, I'll let you go read example 5 later, and you need to, because this technique is a little awkward at first, and you will have to be able to get good at this technique, okay? So, for 64, we have the integral of x times the square root of 2x plus 1 dx. No trig functions to worry about, so we don't have to decide if it should be a theta. Oh, and by the way, I might have gone past this too fast. Isn't that kind of cool? Since sine and cosine are derivatives and antiderivatives of each other, it's fairly common to let u, if you have sine and cosine in the same integrand, to let u equal one of them. Du then captures the other one, and it all kind of works out. Okay? So, back to this. No sine, no cosine, nothing like that. So maybe an exponent, or maybe a quantity with an exponent on it. Do we have a quantity with an exponent on it? 2x plus 1. Because 2x plus 1 is a quantity that has an exponent of 1/2 on it. So we let u equal 2x plus 1. If that's what we let u equal, what does du equal? To what? 2 dx. And let's pause for a moment. I don't have a 2, right? So I'd like to get rid of the 2. What do? So 1/2 du equals dx. And now let's see if we can do our substitution. Don't write this down yet. So we'd have the integral of, all right, let's take care of the u part. The square root of 2x plus 1 can be replaced with the square root of u. Then we need to replace dx. What do we replace dx with? 1/2 du. And look, we've still got that x. You happy with that? No. We can't deal with an integrand that has an x and a u in it. Okay? So we have to replace the x. We have to. We have to replace the x so that it's an expression with u instead. Well, we can do that. See where we have u equals 2x plus 1? Solve it for x, and then you'll know what to replace x with. So that's what I've got going. Here's a little arrow. If u equals 2x plus 1, solve it for x. So I subtracted 1 from both sides. Then I'm going to divide both sides by 2, or multiply both sides by 1/2. And that means that instead of x, I can replace that with 1/2 times u minus 1. Yeah, that's what we'll end up getting. Okay? Everybody with me? So, let's redo this substitution. I'm happy with the 1/2 out in front. I'm happy with the integral sign. I need to leave a space. Well, I'll just go ahead and do it. I need to replace x with 1/2, which I can factor out in front, times u minus 1. I was perfectly happy with the square root of u, and I'm happy with du. So that's our new problem. So I've got 1/2 times 1/2 times the integral of u minus 1 times the square root of u du. And I'm not ready to integrate yet. I need to simplify because that's got a product. There is no product rule for integration. Okay? So, and you can see here when I wrote it in pencil, I didn't factor that 1/2 out yet, but I'm going to now. 1/2 times 1/2 is 1/4 times the integral. And I am not doing calculus here. I'm not taking the integral. I'm just distributing that square root of u. Now, the square root of u is the same thing as u to the 1/2, correct? So I'm multiplying u to the 1/2 times u. So that'll be u to the 3/2. And then I'm multiplying u to the 1/2 times -1. So that'd be negative u to the 1/2. And du is just kind of hanging out. You with me? Okay. Can we take the antiderivative of that? Yeah, we can. So we finally have changed this into something that we can find the antiderivative of. So I've got the 1/4 out in front, u to the 3/2, add 1 to the exponent, make it a 5/2, divide by 5/2, which means multiply by 2/5, minus, and then the u to the 1/2 to get its antiderivative. Add 1 to that exponent, you get a 3/2, divide by 3/2 by multiplying by 2/3. Don't forget, plus c. I don't want u in my answer. I want what u equals, 2x plus 1. So I replace both of those u's with 2x plus 1. And now we come to a decision. Can I simplify that? It all depends on what you mean by simplify. If you actually take the word simplify to mean make it simpler, I can't. I can do all kinds of different things. I can distribute that 1/4. I can then mess around with the fractions and try to get a common denominator. But even then, I can't really add those together because they're unlike terms because the 2x plus 1 has different exponents. I could factor a 2x plus 1 quantity of the 3/2 out. And so do any of these things actually make things simpler? No. Now, I don't know what the back of the book would have as this answer, okay? But I'm pretty happy with that. So I'm going to leave it there. Any questions on 64? All right. Alex? No. All right. Questions from 1 through 39 odd. 27. All right, on 27. You can work this without using a u simply by doing a little factoring. All right, I'll show you what I did here. That'd be the integral. That'd be 1 over the square root of 2 times 1 over the square root of x dx. So I can make that 1 over the square root of 2 times the integral of x to the negative 1/2 dx. That gets me here. And I can work out the rest of that problem and I never did a substitution. Can you follow me on that? Mm-hmm. Or, so are you with me on that? Can you follow that? I can use a u here, okay? I can let u equal 2x. And if I let u equal 2x, then du equals 2dx. Well, as you see, you don't have a spare factor of 2 in your problem, so you can make that 1/2 du equals dx. So that's 1/2 out in front times the integral of 1 over the square root of u du. Can we work that? Yeah. That 1 over square root of u is u to the negative 1/2. Then you power rule it, and you put it back in terms of that. So I like that problem because you get to see that you get the same answer either way. Two completely different techniques, exact same answer. Number 5. All right, on number 5, all they wanted us to do was set it up. And never get yourself in a situation where you say something like, let u equal x. Because if all you're doing is replacing one letter with another, have you actually changed anything to turn it into something different? You just put a different letter. So that's no good. Now, let u equal the tangent of x. Why on earth is that the one I chose? Well, because the next thing I do is compute du, correct? The derivative of tangent is secant squared, which is what I have in my problem. Now, when I've done that, I've done everything the directions asked me to do. But let's go ahead and let's rewrite this thing. So, you with me on what I have written here in pencil? So that means then that this tangent squared x becomes u squared. And then I think the coolest part of all this, secant squared x dx is du. And that just horrible looking integral, it's a product, it's got trig functions. The trig functions actually have exponents on them. Turns into something easy. So then we can make that 1/3 u to the third plus c. So our answer would be 1/3 tangent cubed x plus c. Okay? All right. What else? $33. All right, on 33, I did not use a u. I simply distributed that square root of x. That turns it into something where I can use the power rule in both of those terms. 33. It seems unfair to all of a sudden give you a problem where you don't need substitution, doesn't it? In fact, I couldn't get it. I couldn't figure out a u that worked. Could you? Yeah. So we okay with 33? Take a look at 35 while we're here. All right, this one's solving a differential equation. So we multiply both sides by dx to get here. Then we take the integral of both sides. That gets us here. The integral of dy is y. And then look what I did there. I broke that up into two separate integrals because to find the integral of, or find the antiderivative of 4x, I don't need a substitution. In fact, rewriting, having a substitution, turning that into terms of u would probably make that really complicated, wouldn't it? I've got something that's simple to find the antiderivative of. Why would I want to risk making it complicated? Well, I don't. So I went ahead and broke this up, made it the integral of 4x dx plus the integral of all the rest of that dx. So for the integral of 4x dx, I just bide my time, and eventually I turn that into 2x squared. And then for the integral of the other, I do make a substitution. I let u equal 16 minus x squared. It's a quantity with an exponent on it, so that's a pretty good guess. Then I figure out what du equals. Du was off by what I wanted. It was off from what I wanted by a constant, wasn't it? As long as it's only off by that, I can multiply to turn it into the constant I want. So I wanted a constant of 4. I had a constant of negative 2, so I multiply both sides by negative 2. Then I can do the substitution and see if you can follow the rest of that. We okay with 33 and 35? Well, because look what I needed to replace. I needed to replace 4x dx. But look what du equals, negative 2x dx. So I need to solve, I need to get the right side to be what needs to be replaced. The right side needs to be 4x dx.
So once we find out what you, whatever's left, that
Needs to be replaced as well. It's du or some factor of du, right? Or some product of du and some constant.
what is it when you take a voice?
All right, that's what I do to get du. But look, du, the very first example we did of this, du's all we needed. The rest of the problem equaled du. But see, the rest of the problem, 4x dx, doesn't equal du. What I have to replace is what I just circled in red. So I need to somehow replace what has the check mark next to it, or need to turn what has the check mark next to it into 4x dx. All right. The very first ones we did, it was all nice and easy because they gave us the rest of the problem to be replaced by du. Now we're having to work for it. Okay? All right, what else? Any others? We didn't do even ones. All right, on 19. All right, following the guidelines, I'm going to let u equal a quantity with an exponent on it. So let u equal 1 minus x squared. Once I have u, I need to compute du. So du is going to be negative 2x dx. But like we just got through talking about, what needs to be replaced is x dx. So I don't want that negative 2. So I'll multiply both sides by negative 1/2. So now, see how I have, and this isn't just for this problem. I'm trying to teach you something in general here. See how what I have circled in red in the problem is now the exact same thing as what I have circled in red working out with my u du. That means I can replace x dx with what it equals. Okay? That's your goal. Your goal is to replace everything in the original integrand with u's and du's, or constants. Constants are good. Okay? So the denominator here of 1 minus x squared quantity cubed becomes u cubed. And then what's circled in red gets replaced with negative 1/2 du. Now, you might wonder, well, in fact, let me do this. Let me do it this way. So, when I'm doing my substitution, say, okay, I like to tackle the u portion first. So down here, 1 minus x squared is u, so that's u cubed. And then I'm going to tackle the x dx. Well, x dx is replaced with negative 1/2 du. And look, I've got a blank for the numerator. Well, I can't leave a blank. Does multiplying by 1 change the value of anything? So, multiply by 1. Okay? Make sense? All right. That gets me there, and I think it should be fairly straightforward from there. I don't need to figure out what x is equal to because I'm already replacing it. Any others? Chain rule. If u equals 1 minus x squared, the derivative of that is going to be the derivative, that's supposed to be d over dx, of 1 minus x squared, and then the chain rule can always be used times the derivative of x. So, I, I don't really understand.
So, looking at that, how do you know
That means change the expression so that it's in terms of u, and then the rest of the integrand has to work out to be g prime of x dx or some factor thereof so that it can be replaced with du. I mean, we're still at the point where if they don't make these up just right, we can't figure out how to integrate them. Okay? All right. Here's what you need to do today. Page 304, 2 through 70, even.